Okay, everyone. Now we'll move into the application of electrolysis. Let's start with looking at lecture exercise 12.1, electrolytic purification of copper. This is actually an important application for electrolysis. So you start off with the impure copper. In this example, you have zinc and silver as impurities. Okay, so the impure copper is actually placed as the anode, okay, of which when you pass a current through, the copper will be oxidized, okay, and it forms copper 2 plus, goes into electrolyte, and it will move over to the cathode and get reduced to pure copper. So the impure copper is the anode, and at the cathode you have pure copper. So let us see what happens to the impurities in this case. Alright, in this example, note that you have zinc and silver as impurities. Okay, so now we'll go into the data booklet and quote the three reduction potentials. Okay, that is for zinc 2 plus zinc, copper 2 plus copper, silver plus to silver. Okay, so now take note that for this particular cell, the voltage will be adjusted such that we can oxidize copper to copper 2 plus. Okay, because we want the copper to dissolve so that it can get purified at the cathode. So the voltage will be adjusted such that your copper will be oxidized to copper 2 plus. So if you look at the reduction potentials, since the reduction potential for silver plus silver is more positive, okay, than that for copper, right, it will not be oxidized. Okay, the more negative the reduction potential, the more easily it is oxidized. So for the silver plus to silver is more positive than copper, so it will not be oxidized. Okay, so right now we know that copper is going to oxidize to copper 2 plus, silver is not going to be oxidized. Okay, let's see what happens to zinc. Reduction potential for zinc 2 plus zinc is actually more negative than that of copper. Okay, so zinc will actually be preferentially oxidized than copper. Okay, so when you try and oxidize copper, the zinc would that naturally be oxidized. Okay, so take note that over here we are trying to compare the reduction potentials. Okay, so this is what is happening at the anode. Copper will be oxidized to copper 2 plus 2E. Alright, take note that you write this equation with a single arrow. At the same time, the zinc gets oxidized and it goes into the electrolyte. Okay, remember we were saying that silver metal will not be oxidized. Okay, it should be D here. Silver metal will not be oxidized. Okay, and therefore it just fall to the bottom of the container as anode sludge. Okay, because as the copper and zinc dissolves to form the aqueous ions, it will not be able to hold the silver metal there. So the silver metal falls off as anode sludge. So this is what is happening at the anode. Now moving on to the cathode. Okay, so we now have copper 2 plus and zinc 2 plus in the electrolyte. Alright, so let's see what happens at the cathode. Who is the one that will be reduced? Okay, if you look at the reduction potentials again, copper 2 plus copper is positive 0.34, zinc is the one with minus 0.76. So reduction potential for copper 2 plus to copper, okay, is actually more positive than that for zinc 2 plus to zinc. Okay, of course you can say that the reduction potential for zinc 2 plus to zinc is less positive than that of copper. Okay, so this means that the zinc 2 plus will not be reduced, it will just remain in the solution as aqueous ions. Okay, as the copper 2 plus gets reduced to form copper at the cathode. So this will then allow us to have a pure copper cathode now. Okay, and therefore we can use this process to purify copper. Okay, and it's actually a very important and useful industrial process. Understand?